This is Fahad here, and today I'm going to talk about how a neural network stores so much information. Let's look at what a neural network is. If you think about the output of a single neuron in a very large neural network, it's asking a question about the input, a single question that has a yes answer, a no answer, or somewhere in between. This could be any output, but after applying an activation function, this could be somewhere between 0 and 1 after normalization. So if it's an input like, let's say, is it a person? Yes or no? I'll make this one a 1 and this one 0. So for this sort of input, it would be either 1 or very close to 1. If the input is something else, that's my impression of a cat. If the input is something like this, the answer would be 0 or close to 0. This is a single neuron. In a large neural network, there are hundreds of billions, perhaps even trillions of these parameters or weights to various inputs. If you consider this as parts of an input, you can apply it to these parameters. There's an activation function, you get an output, and then this goes into another layer. At the final layer, we get some sort of input similar to, is it this token or that token? Now let's consider two neurons, neuron 1 and neuron 2. You can have anywhere between 0 or 1. In this space, you can have anything in this entire space. In theory, it could be the entire space above, and it could even be extended to the other side. This is the entire space where we could have an answer like this, an answer like this, something like this. If this is a two-dimensional space, which in this case, this whiteboard is, you can encode perhaps two independent pieces of information. If one is in this direction, the other completely independent piece of information it can store or represent is this. If one is this direction, the other independent direction is always something that's at 90 degrees here. So this could be another independent piece of information that this network could encode. The other direction is this negative of the same thing. So now in these two dimensions, it seems like we can only encode two pieces of information here. Why? Because if we have anything like this, it has some element of this piece of information and some element of this piece of information. So they get mixed. Neural networks, by their very nature, can tolerate a little bit of noise. So if you have two vectors, they're not exactly at right angle, but almost at right angles, a neural network can still handle this information. Let's look at independent pieces of information in two-dimensional space. Say we've got these two dimensions. This is a unit circle. You take any two random points on this unit circle. Let's say this is one direction and this is another direction. The angle is maybe a little more than 90 degrees, maybe a little less. The angle could be anywhere between 0 and 180 degrees, or let's not go into radians. Between 0 and 180 degrees. But for two pieces of information to be completely independent, this has to be exactly 90 degrees. Even if we tolerate a little bit of noise and say, you know what, we don't need exactly 90 degrees. Maybe we can tolerate a few degrees here and there. When you increase the number of dimensions from 2 dimensions to, let's say, 3 dimensions, this is my representation of a sphere. It's like a ball in 3 dimensions. Now we take any 2 points on this sphere and draw vectors from the origin to these 2 points. The angle between these, theta, if you take 1,000 or 1,000,000 random points, turns out to be a lot closer to 90 degrees, or at least the probability of the angle being 90 degrees is far higher. But if you keep increasing the number of dimensions, remember that in large neural networks or in large language models, we have got trillions of weights, and each layer has perhaps thousands of neurons. So each layer in a neural network has thousands of dimensions or thousands of yes-no questions in each layer. A combination of all of those hundreds or thousands of layers means that there's so many yes-no questions being asked. And they could be independent, they could be nearly independent. It turns out that for higher dimensions, this thing becomes very close to 90 degrees. For very high dimensional. What this really means is that if you tolerate just a bit of noise without it being too far off 90 degrees, it's almost an independent piece of information. If I select a vector that's just a little bit less than 90 degrees, how many vectors can I fit within a 2-dimensional space? It's still 2 nearly perpendicular vectors. But in a 1,000 dimensions space, I would fit way more than 1,000 vectors that are nearly 90 degrees to each other. This quantity of very large or high dimensional spaces allows a neural network to encode a huge number of pieces of information within a few neurons. When I say a few, there are still thousands or tens of thousands or billions of neurons. If you think about a billion parameters with millions of neurons in between, you can fit way more information in a million neurons than there are number of dimensions in that space or number of neurons. And you may be able to fit thousands or millions of times more information in that space than there are a number of neurons. That's why as you scale the number of neurons and pieces of information, initially perhaps it's linear, but very soon this really explodes. This is one of the scaling laws that people discuss regarding large language models and neural networks. The information you can store as you increase the number of neurons or parameters explodes exponentially. That's why you can ask pretty much any question of a large language model and get a plausible answer. The amount of information a neural network with very large number of neurons stores is way larger than the number of neurons. And this is how a neural network stores a very large amount of information. Thank you.